Back. We were looking at various graphs of exponential functions. So continuing with the properties, when b and a are two bases, b greater than a and both greater than 1, then b power x is greater than a power x. So higher the base, higher the value, as long as the bases were greater than 1. Okay. This happens when x is positive. When x is negative, they flip. B power x is less than a power x. Notice 3 is greater than 2. 3 power x is greater than 2 power x, right? When x is greater than 0. On the negative side, when x is negative, 3 power x is lower than 2 power x. Okay. On the other hand, if b and a are less than 1, b less than a less than 1, then b power x is smaller than a power x, smaller the base, right? But this happens when x is positive, whereas when x is negative, the inequality flips. All right. So look at 1/3. 1/3 is actually smaller than 1/2. So on the positive values of x, 1/3 power x is lower than half power x. Whereas when x is negative, 1/3 power x is higher than half power x. Okay. The whole point is, as long as if a base b is bigger than base a, its power, its exponent will be greater than a power x. That will happen for x positive. Likewise here, see, a is bigger than b, so a power x is bigger than b power x for x positive. For x negative, they flip. All right. Now, here is a comparison of exponential function with monomial functions. Okay. This is y equals x squared. X squared. X squared is a parabola. So notice you have an exponent. It's lower than x squared at some point. Then it goes higher. And we can't see very clearly, but 2 power x is actually lower than x squared up to some point, and then it shoots up. The point is exponential is faster growing than x squared beyond a point. All right. So this is fairly common. No matter what power of x, exponential might be lower in pieces, but for large enough x, the exponential grows faster than any monomial, right? Positive coefficients and so on and so forth. So, when are they equal? When x is 2, x is 4, x squared is 2 power x. You can check. Between 2 and 4, so that's where x is 2 and that's somewhere there is x is 4. X squared, the parabola is higher than 2 power x. But beyond 4, exponential takes off. So beyond a certain number, exponential is going to be higher than any polynomial, in fact. Now, theorem 1, this summarizes all that we have been saying so far. If b is greater than 0, b not equal 1, then fx is b power x is a continuous function. Now, this is a bit of work, but it's an analysis. We have used some of it, but anyhow, let's continue. It is a continuous function with domain all the set of all real numbers and a range 0 to infinity, because notice your exponential is always above the x-axis and it hits everybody above the x-axis. You see, very low to very high and so on, except the case when you have a constant function. Constant function has only one point in the range, whereas this is where we need to exclude that constant case. So for non-constant case, you have range all of 0 to infinity, open 0 to infinity. In particular, b power x is greater than 0 for all x. Now if b is between 0 and 1, then the exponential is a decreasing function. If b is greater than 1, the exponential is an increasing function. For any two bases, a and b, positive bases, any real numbers xy, you have these power rules. B power x plus y is b power x times b power y. B power x minus y is b power x over b power y. B power x, the whole power y, is b power xy. Now if you have product of two bases, ab power x, that is a power x, b power x. Alright. So these are standard results you already know. In addition, we have learned a little bit about exponential functions. Now here is theorem 2. From the graphs of the exponential functions we see, if your base is greater than 1, then as x approaches infinity, b power x is infinity, and as x approaches negative infinity, b power x is 0. Let's see. Here, base is greater than 1. So these are the two cases. So on the right, these curves go to positive infinity. On the left, these curves go close to the x-axis. That's all we are saying here. Okay? When the base is greater than 1, to the right, the curve approaches infinity, and to the left, the curve approaches 0. On the flip side, when your base is between 0 and 1, that is, it's small, smaller than 1, then on the right, it goes close to 0. On the left, it goes to infinity. Okay? So limit x approaching infinity of b power x is 0, and limit x approaching negative infinity b power x is infinity. So precisely, when your base is less than 1, well, of course, positive base, on the left, as x approaches negative infinity, your curve goes to positive infinity. When x approaches positive infinity, your curve approaches 0. All right, now we want to introduce derivatives of exponential functions. So choose any base. Base greater than 0, base not 0. Oh, I'm sorry, it should be base not 1. Why? Because if base were 1, then you have a constant function. You know derivative of constant function is 0, nothing much to do. So assume that your base is not 1. Okay? So make sure that's base not 1. Okay? So consider the exponential function. Well, what's the derivative first at 0? Okay? By definition, it is limit h approaching 0, f of 0 plus h minus f of 0 by h minus 0. So 0 plus h is simply h. So function is base power x. So limit h approaching 0, b power h minus 1 over h. This is the derivative at 0. At 0. Now, for any x not 0, what would I do? Well, it's the same rule. Limit h approaching 0, f of x plus h minus fx over h minus 0. Well, f is the exponential. So b power x plus h minus b power x over simply h. Okay. Now, b power x plus h is b power x, b power h. Minus b power x as before over h. Notice b power x is common, so get that factor out. B power x times parenthesis b power h minus 1 the whole over h. So this limit is with respect to h going to 0. So b power x can be completely brought out. We did. So bring it out. Limit h approaching 0, b power h minus 1 over h. This is something we just saw. What was that? That is derivative as 0. So it is b power x times f prime at 0. This is an important result. F prime at x is the original function exponential f prime at 0. So to find the derivative at x, all you need is to find the derivative at 0. Whatever that number is, that times b power x is your actual derivative. So this, by the way, derivative at 0 can be calculated using a calculator. Say take base equals to, punch in several values of h, say 0 0.5, 0 0.4, 0 0.3, 0 0.1, whatever, 0 0.0001, and see what happens. It will approximate to 0.69. That is, derivative of the exponential function 2 power x is 2 power x times derivative at 0. All right. Likewise, when base is 3, use your calculator, base is 3, and find different values of as h approaches 0. H can be 0 0.5, 0 0.4, and so on, right? You will see that this limit approximates to 1.10. Okay. 1.10 is the derivative at 0. What is the general derivative of the exponential function base 3? General derivative is approximately whatever this is, 1.10 times the function itself. So derivative is a scalar, it's a number times the function itself. All right. So I will continue in our next video what the Euler number does.